I think. Thank you very much for the invitation. I'm very happy to see that this is a conference happening on site after such a long time. Okay, so yes, here is the fantastic remote control. Okay, so the title of my talk has already been announced, and this is joint work with Peter Balint from Budapest University and Henk Braun from Vienna University. Okay. Oh. Yes. So first, I will give us a short overview of what I'm going to talk about. This is going to be about limit laws for infinite horizons Lorentz gases when the time goes to infinity and the size of the scatterer goes to 0, and this happens simultaneously. Obviously, we need some pace at which the size of the scatterer goes to 0 and the time goes to infinity. So what the plan for today's talk is, first I will recall some very well-known results for the fixed configuration, so fixed position of the scatterers and fixed size of the fixed radius of the scatterers, and then I will recall some results that in the Boltzmann-Grad type situation that will allow me to place the new result in context, and finally state the new result explaining what are the challenges. Okay, and to start with, I know you have attended, most of you have attended Vivian's talks on Tuesday, Vivian Baladi's talk on Tuesday, and therefore a lot of familiarity with the notions that will be briefly recalled here is I kind of assume it. Okay, so to make the whole thing easier with the picture, I will recall what happens in one dimension, so the so-called tubular billiard map. So this is a model of particles moving and bouncing elastically in a periodic grid of scatterers. People do refer to these type of models as Lorentz gases, although there is a lot of unclear terminology in the literature, and I'm not going to make justice to that. So what do I have here? I mentioned periodic grid of scatterers, and this is due to the okay, I can do this, but better not. Yes. Okay, so this is due to the periodic configuration of the scatterers, and precisely due to this periodic configuration, the movement of the particle in every cell. So first of all, due to this periodic configuration, we can actually divide this grid in cells, which are going to be the same, and the movement of the particle in every cell is going to be again the same, which actually means that you have the same dynamics in every cell. And I can't really point to what's going on here, but I can say in words that basically if you start on a cell, well, the particle is doing some movement, is bouncing, is against the next scatterer, and at some point might decide to go to another cell. And the function that is going to tell us how you essentially move in Z in this case is the so-called displacement function, which gives precisely this, the difference of the cell numbers between collisions. And the terminology I shall use here is that a single cell will be labeled by M, and this displacement function has an index there with a rho. What rho, it shouldn't have been really on this slide, but the meaning of rho is going to be clear in the next slides. So this is the displacement function, which tells us how we move in Z. And one other important thing that I want to say here, this is finite horizon, meaning that if you take any single line you can't draw any single line that doesn't intersect the scatterers. So that actually tells us that this displacement function is bounded. So essentially there is very little room for movement. That's the way I would put it. Okay, so in the infinite horizon situation, we have exactly the opposite. There is, you can certainly draw lines that do not intersect the scatterers. Okay, and finally, now I'm going to this setup, which I will stick to. Again, infinite horizon. This is the setup I'm interested in. And with this picture, I can already say a few words of the problem I'm interested in. So this is a fixed configuration of the scatterer, and we are interested in shrinking the size of the scatterer and see what type of limit loss, whether you can recover the previous one for fixed size or not. Okay, and one other thing that I shall say here, due to so you are in infinite horizon, you have infinite horizon direction, which actually means that, to introduce some other terminology that I will use later on, which means that there are 4 main corridors, and of course these four corridors are counted up to multiple corridors. Okay, so now to introduce a bit more of the notation, and also say something about the entire dynamics in the end. Lorentz gas can be viewed as a ZD extension, so D being 1 or 2, of the dynamics on the cell. The phase space, the dynamics on the cell, you have been introduced to this on Tuesday by Viviane Valadi, is the so-called, the famous Sinai billiard. And the phase space here is simply given by, you take the boundary of the scatterer and multiply it with minus pi on 2, pi on 2, which simply gives you the reflection angle. So here, for simplicity, I will stick to the scenario where the scatterers are round disks at the origin with radius rho. So the radius, this rho that will appear throughout is precisely the radius of the scatterer. Okay, so I have already mentioned what this displacement function is telling us, that it tells us how we move on ZD, from which point in ZD to which one you move. And now an important thing for me is that although everything is deterministic in everything I said so far, no randomness whatsoever, this kappa function is going, this displacement function is going to obey the same law as a random walk in ZD. And essentially, this is simply saying you can, to some extent, view everything as the analog of a random walk on ZD with transition probabilities given so Z, you go from Z to Z plus N, and the transition probability will be equal with precisely the measure of kappa equal N. Okay. Of crucial importance for proving such law were the work of Chernov and Young, which I will mention later on again. And one other thing that I shall stress on is in the infinite horizon situation, this kappa function is not going to be bounded as it happens to be in the finite horizon case, but unbounded and in fact not L2, which, as I will explain later on, makes the crucial change between diffusive behavior and super diffusive behavior. Okay. Now, something more about the entire dynamics, since I'm in the end also after infinite measure preserving systems. So as a ZD extension, the entire dynamics is an infinite measure preserving one. And the phase space is simply this M hat, which I denote here by M hat, is M being the cell, and cross Z D equal to, as I wrote it here. And so, as I mentioned, this is essentially, so here is the equation for T hat rho, which actually tells us that we extend by kappa. So the first component of this Q product, if you want, is that of the Sinai billiard, and the second one is extends by kappa. So you have L, the number of the cell, and you add kappa n to it, and this is already for the iterate. For n equal 1, you just add kappa, and here is already for the iterate of the dynamics. Kappa n here is just the usual Birkhoff sum for the Sinai billiard. Okay, and as I said, this preserves the measure is infinite, the reason being obvious because the product measure is mu cross Lebesgue on ZD. Okay, now, although that's not the scenario I want to focus on, I will start recalling very briefly what are the type of stochastic laws one has in the finite horizon situation. So in the first place, and here I suppress anywhere the appearance of this rho because it's irrelevant for the scenario, for the story I'm trying to tell. Obviously, so I told you that we were after shrinking the radius of the scatterer. In a finite horizon situation, in a fixed configuration, no one can do that. So this is why I'm suppressing here anything like rho. Okay, so in the first place here we have diffusive behavior, which actually a first characterization is in terms of the central limit theorem. So we have kappa n scaled by the usual square root of n. Converges to a Gaussian with mean 0 and variance sigma. And this was proved long ago by Bunomovich and Sinai. And since then, several refinements are known. And also, I shall add here that the convergence to Brownian motion, so the invariance principle, the functional limit theorem is also well known. And two refinements to the statements are the following. The first one is a local central limit theorem, which is proved by Sash and Varju. So it simply tells us we are in dimension 2, I recall that. So it tells us that if we look at the measure of kappa n being 0, we need to scale by the square root of n to converge to the density evaluated as 0, where this density is, of course, the density of the Gaussian that we have in the central limit theorem. And so this would be a first refinement. A second refinement, I mentioned the weak invariance principle, but much more than that is known, which is the almost sure invariance principle, and this was established by various people with different methods. And finally, important for the story that I'm essentially after, is the mixing for the entire dynamics. So what happens, I'm trying to do a smart thing. So what happens in in an infinite measure situation, this quantity here simply goes to 0. But due to this equality that we have here, and due to the fact that we know what the local CLT looks like, that actually tells us that if we multiply by this number here, we'll have convergence to a non-trivial limit. So this is mixing. Okay, so, and then more than this is known, which is speed in all this local limit theorem and mixing. Okay, so this is the finite horizon. Now I move to the scenario after, where kappa becomes unbounded, and here, so infinite horizon, and rho comes back here, and this rho is what? No, it doesn't work like that. So this, no. Yes, this rho here is in the interval 0, half necessarily, because otherwise you are in the finite horizon. And that's obvious, just think that the scatterers are simply fixed at lattice points in ZD. So if you have the radius equal a half there, then you are back to the finite horizon, because the scatterers simply touch each other. No, I'm doing something funny with this thing. Yes, okay. So, so I mentioned the super diffusive behavior, and the first statement is that in this case, the first characterization of this super diffusive behavior is that instead of, you still have CLT, but what happens instead of having the usual CLT, you have the CLT with non-standard normalization. Since kappa just fails to be L2. So we have convergence again to a random variable, to a Gaussian random variable with mean 0 and variance sigma rho, and the dependence on rho here is important. I will come back to it. This sigma rho is, of course, obtained via summation over corridors. So you remember the picture I had before with the 4 infinite horizon directions, so summing over all those corridors. And So this is the CLT statement with the non-standard normalization, but more than that is known, and this CLT was never really proved by itself. It was proved along with some other refinements. In fact, the refinements are proof and the CLT follows. Okay, so the first method is the so-called spectral method on some objects called Young towers. What at this point, since I haven't introduced any terminology, and I expect that not all of you, I do not know if all of you have attended Vivian's talk on Tuesday. I will just say that what the spectral method means just means that this is the analog in the dynamical system of what is very well known in probability as the characteristic function method. Of course, you need a lot of properties of the so-called transfer operator, and this is where the spectral theory comes in, spectral properties, spectral methods come in. But for the time being, so method one, via using these spectral methods, you don't just prove a CLT, but you prove a local limit theorem. And here is the statement. So this is again as before, except that this time the scaling is going to be n log n. And we have again convergence to the density, so the measure of kappa n equals 0, scaled by this quantity n log n converges to the density of the Gaussian. And this result was established by Sass and Variu, and they do exploit essentially the existence of the Young tower and all the structure that goes in it. So essentially it was established that the Sinai billiard can be modeled by a Young tower, and on Young tower you have a lot of structure including a fantastic Banach space on which transfer operator can act. Good, so this is the result, and as I said, this exploits the existence of a Young tower, and more than that, it exploits, it uses an abstract result established by Balit and Güzel. Okay, so this is method one. Method one, the benefit of it that it doesn't give just the CLT, but it gives a local version. Okay, then also within this method one, more is known, namely speed in the local limit theorem, and due to the story that I said before, the relation between mixing and the local limit theorem, one can obtain mixing and actually speed of mixing as well, and these were obtained in some work in 2021. And again, is this equation here that makes the relationship between the local limit theorem and mixing possible. Okay, so this is method one. Now, second method is the standard pair, which actually exploits certain correlation, exponential correlation for the sequence kappa rho composed with t rho to the n. So rho, I recall, once again, is the size of the scatterer. And using this, which is actually due to Dogopiat, Chernov and Dogopiat, in 2009, using this standard pair technique, they established not only the central limit theorem, but actually a refined version of it, which is the weak invariance principle. So again, as I said before, convergence to Brownian motion, except that the scaling is once again the one that one expects it to be due to the infinite horizon. Okay, now I will come back a bit in more detail to all of this and make this statement a bit more precise, but for the time being, let me say something about method one again. So this method one, I refer to it initially as a spectral method on some spectral method, and this is usually referred to as Nagaev-Givash method. And what does this come down to? Well, it comes down to being able to control this object here, the transfer operator, which has been introduced in many talks, in some sense, in the sense of having the spectral gap property, and for that you need some Banach space. And the Nagaev-Givash method says that, okay, you can do a perturbation of this operator, and the reason why, and provided that you also have good properties for this operator, along with something else which I shall mention in a second, then you are able to use this fantastic equation here, which tells you that if you want to look at the characteristic function, well, you just have to look at the integral of this transfer operator. So this is well known for people in dynamics, but since the audience is mixed, I recall some generalities. So the Nagaev-Givash method doesn't only require this spectral gap property, which I didn't state, but I alluded to, but it also requires some good continuity properties of the family of these perturb operators. So at least for the methods to even make sense, one needs to show that this quantity here goes to 0, st goes to 0, in some norm, well, in the norm of the Banach space you work with, but less than that is possible. However, so this convergence to 0, in fact, it's useless by itself. In practice, much more is needed, at least if one is after getting something like a local limit theorem. I'm not aware of any method where you can actually just use this bare continuity statement and do something with it. Okay, so so far, just to summarize what I kind of said before, this has been done on the Young Banach space using the on the Young tower using the existence of the Young Banach space, and this was done by Sass and Varyu. Okay, so in short, this gives more than CLT and namely LLT. Okay. This is a note or a remark which I shall use in a bit. This spectral gap property has also been established in anisotropic Banach spaces of distribution, which were introduced which were recalled by Viviane Baladi on Tuesday. These spaces were introduced by, well, let me put it that way, successfully used for the billiard dynamics by Demers and Zhang using a framework of Demers and Liverani. However, this is just about the spectral gap. Recall that I have mentioned that in order to carry out that method 1, which is the Nagaev-Givash, you need more than that, you need continuity properties. That has not been done even for fixed rho, for the infinite horizon billiard. Okay, so this was a side note, and now I come back to method 2. So I mentioned that the crucial result that was the important result that was established by Chernov and Dogopiat is this correlation function of kappa index rho, and it says that well, for every fixed rho, so this is in the infinite horizon situation, once again, to recall that, for every rho in this interval, making sure that you have it, you are in the infinite horizon, there exists a theta, depending on this rho, which is the size of the scatterer, once again, so in between that is in less than 1, and so that you have this, this correlation function here. So you have exponential decay. Now, using this exponential decay, going from this to CLT and respectively to the weak invariance principle, this is completely classic. You have two methods. You have so for the CLT there is this well-known method via big small blocks type arguments. And then the step from CLT to the invariance principle, provided that you have the CLT, is basically just a classical verifying a certain tightness condition. So the step, these two Bs that were established by Chernov and Dogopiat were not the hard Bs. What I'm trying to say that the essence of their work is to establish this exponential correlation for this sequence, kappa rho. Okay, so good. Now, so far done with the, how many more minutes do I have? I see no clock here.
Maybe 2. Or 4.
Okay.
Let's say 4. I mean, we start late.
Okay. Then I didn't realize. So I will just recall then that okay. So in the Boltzmann-Grad limit scenario, what people do, they look at the same sequence of random variables kappa and rho. And so it's not only about time going to infinity as before, but what do? They let rho go to 0 first, which is followed by n going to infinity. Cutting the story short, we have clarified in this work that the two. So here we have convergence to CLT, so this is the Gaussian with some variance sigma. But before I mentioned this sigma rho, so the variance that depends on sigma. So this is, we verified how the two relate. This is of course just a calculation, an easy calculation, but we had to understand that. So the open problem, as they state in their paper, one open problem is to consider the joint limit. And again, I stress that in this scenario we have fixed configuration of scatterers. However, how is this possible? I will not have time to go into because I want to state my result. So in any case, the limit path is rho goes to 0 first, followed by n go to infinity. And what happens, we are interested in I recall again the picture, we are interested in shrinking the size of the scatterers, letting this go to 0. And the first problem which appear in the picture, you see that, well, you see here that and more, this is the next one, I will not press the next button. So what happens, the more you shrink the size of the scatterer, the radius of the scatterer, the more and more corridors open up. And this is a main source of difficulty for us. And okay, now to make sure that I state the main result at least. So this is what we obtain. We are able to look at this fixed size configuration, but letting rho go to 0 in a certain relationship with time. So as a joint limit, so in some sense this gives us the first result that is in between the Sash and Vajou result and the result of Markov and Todt. So you let simultaneously n go to infinity and rho go to 0, but you have to do that along a certain path. So we established that there exists a function m of rho that goes to infinity as rho goes to 0, so that when you have the scaling by the usual, obviously in this scaling rho is going to appear because rho is going to 0. Okay, and this is the precise characterization of the limit path, and we have a bit more information on this m of rho, which is exactly here. So m of rho that gives us a precise, an explicit characterization of the limit path has this form here. So this theta index rho here, it's exactly the quantity that appears in the exponential correlation for the kappa index rho function. So this is one term, and the next one is C times rho to the power minus 2, with rho being the size of the scatterer. So this is, so we think that the limit theorem we actually obtain is very explicit in terms of, so the characterization that of all the quantities that appears in this limit theorem are explicit up to this unknown dependence of theta rho on rho. But for the rest of it, this is a complete result. And again, because we do something along the spectral methods, we are able to get not only the CLT, the one that I mentioned before, but the local limit theorem. And finally, we also obtain mixing. And we also have, of course, the weak invariance principle, because basically our method in the end works on, I will say this and I finish. Our method works on these Banach spaces of distribution. This is exactly where we do our analysis. But we also combine our method to be able to control anything because the continuity estimates that we were able to obtain were very poor. We had to combine it with the standard pair technique and get the results. So thank you.
Thank you very much. Are there any questions? Yes, please.
I'm just curious, could you say a bit something more about what didn't enough to use just the Banach space as you need to couple it with the standard pairs technique, or I misunderstood?
Yes, that is correct. So we weren't able to, let me actually jump to the very last slide if it's possible. Okay, so you need to control an eigenvalue. So the continuity estimates that we got were actually very poor in terms of something like t to the mu, where mu is less than a half. If you try to use that directly with the usual techniques, you can't actually do it. So you have to do a lot of decomposition, and several terms that appear in this fantastic expression of the eigenvalue, you have to analyze them with the standard pair technique, trying to squeeze a t out of it. We can talk more. This is technical, but yes, it wasn't enough. The continuity estimates we got were very poor, not enough. Usually you need a t in order to operate freely. So we have that out of, if you take the, let me go here. Yes, so the continuity estimate that we got is exactly this one. Is t to the mu. So we had to control everything in terms of rho as well, but is t to the mu. This mu is less than a half. If you try to use it directly, you have, you have to do something.
Okay,
yeah,
thanks.
Thanks.
So thank you very much. I think we should move on, but before we do, please stay. So in recognition of your invited talk, you're being offered this token of appreciation.
Thank you very much.
Thank you.
Thank you.
Thank you. Okay. Okay, Carlangelo, you can proceed with the second speaker, please.
Okay, so let's go to the second speaker, who's Jacopo De Simoi. And De Simoi also got his PhD in 2009 in Maryland. And his advisor was Dolgopiat. And he has held several postdoc positions in Paris, in Rome, and he is currently associate professor at Toronto. So he started studying Fermi acceleration and the standard map. So these are very standard problems in dynamical system. And then he has been working on integrable billiard, statistical property of partial hyperbolic system. And in this field, he has obtained several remarkable results, in particular with Abel and Kaloshin. He proved a partial answer to the Birkhoff conjecture for integral billiards. In collaboration with Kaloshin, he started the study of dynamical spectral rigidity for billiard, which is kind of a new twist in the field. And also he has been working, obtaining result on fast-slow dynamical system. So that is actually the argument of his talk, since he will talk about the statistical property of fast-slow partial hyperbolic local diffeomorphism. Exactly. So please, Jacopo, you have the floor.
Thank you so much, Carlangelo, for this nice introduction. I need to thank the organizers for taking care of this nice session and giving me the privilege of giving this talk today. So Dalia mentioned that she's happy to be there in person. I don't have this possibility, but I'm happy to be there in spirit at least. So speaking of privileges, I need to perform this land acknowledgement. Since I'm inviting you guys here in Toronto, I wish to acknowledge the land on which the University of Toronto operates, and for thousands of years it has been the traditional land of the Huron-Wendat, the Seneca and Mississaugas of the Credit River. And today this meeting place is still the home to many indigenous people from across Turtle Island. I'm very grateful to have the opportunity to work on this land. So back to math, what I would like to talk about today is something which you might already have seen if you attended Roberto's talk 2 days ago. So let me just jump in medias res. So let me just jump to the system that I want to study. So as I mentioned, as Carlangelo also mentioned, I'll be talking about partially hyperbolic local diffeos. And I have a very specific example in mind, which I will now put on the blackboard. And this is it. So it's a map on the two torus, which again, you already seen if you attended 2 days ago, the talk was given 2 days ago. So this is a talk on a map on the torus, which has specific properties. In particular, it's a fast-slow system. And what do I mean by that? So you have a fast component, let's put it blue, which is the first variable, or x. And the first variable is undergoing, and now my computer is freezing, of course. The first variable is undergoing, here we go, fast motion, which means that in this specific example, it's driven by expanding map of the torus. So this is just a very classical example of chaotic dynamics, of course. And what about the slow part of the dynamics? Well, the slow part is the second variable, or theta, here. And the second variable here is essentially performing a very mild variation with each step in the dynamics. You're just going to add a little epsilon times some perturbation omega to it every time. So about the conditions that I want to set on this problem, those are essentially very mild. I have some, again, expanding mass, but I need some more specific smoothness properties. The number 4 here is probably not that important, but we definitely need some smoothness, so you can just consider it to be CR, but at least R needs to be larger than 4. So what is the motivation behind this map? Well, there are a couple of motivations, in fact, in mind. What we wanted to do is to study statistical properties of this kind of maps, in particular of partially hyperbolic systems, since most of the results which were available for this work, which is, I should have mentioned, together with Carlangelo Liverani, Christophe Fouquet, Dennis Volk, and Kasum Fernando, in different orders, and we'll try to acknowledge its different contribution when time is due. So what we had in mind when we set up this problem is to obtain statistical properties for this system, whereas at the time, most of the results that were available were results mostly qualitative about ergodic properties or stable ergodicity at most. So if we want to study something which has a very strong statistical properties, one might think that one wants to start from something which already has some very strong statistical property, but this goes exactly in the opposite direction. So we are sitting on the boundary of a map which has very poor statistical properties. So morally, this map F epsilon is perturbation of a very simple map, which is given by a product or a trivial extension, if you want, of a family of expanding maps and the identity. So I say morally here because if I perturb this map, F theta would also be perturbed, but since I assume F theta to be expanding by structural stability, this is also going to be an expanding map, the perturbation. So I can also always somehow glob the perturbation inside F theta and consider the actual perturbation as this part here, which is small in as epsilon is small, and this epsilon being positive essentially sets the stage for considering a family of expanding maps which are weakly coupled. So this is a weak coupling regime of a continuous family of expanding maps. So F theta cross again of a continuous family of expanding maps. So X theta goes to F theta of X theta. So this is a very interesting and classical problem in mathematical physics. Of course, you have some system, and this system is started to be independent, and then you turn on the perturbation, and what you want to answer is what are the statistical properties of this system? Do I have unique equilibrium? What's going on with the perturbed system? So here's the program we set up to. And of course, there was a lot that we didn't know about this problem and a lot that we figured out in this period. So let me just make a few classical remarks about this system. So this system is not directly a skew product unless the family of maps is just a constant family. So this is a more general setting than a skew product. It is a local diffeo. It's not a global diffeo. And as such, this implies in particular the non-existence of unstable manifolds. So if you, for instance, consider the inverse limit, then you can find an invertible system for which you can construct unstable manifolds. When you project them down to the actual system, you find a bunch of unstable manifolds which depend on the history of the point where you're looking at. So there's no unstable manifold. This is just a remark, but it actually will have something consequences that since these are expanding maps, for any parameter theta, I will have a unique absolutely continuous invariant probability, mu theta, which in fact is smooth. So it's given by a smooth density, rho theta. And it's not only smooth in X, it is also true by a result by Gesell and Liverani, that the map, which you start from theta, each parameter, and you look at what the density is. This also has some smoothness properties. You lose something, you get C3, maybe C3 plus alpha or epsilon. But this is just again some side remark, which will be it's useful to keep in mind. All right. So how do we study such things? We have a kind of a common framework, which is a probabilistic idea. You consider the iterate of this map as random variables. So you have a random process now, which it's the modern way of understanding what hyperbolic dynamic is. So you have consider distribution of initial conditions nu, and this gives you the randomness in the system. And then the iterate will be random variables with respect to this distribution of initial conditions. Now, of course, we cannot start from arbitrary distributions, otherwise you don't see any randomness. So if you start from a delta, for instance, you have a completely deterministic system, so that is not going to be interesting from a statistical point of view. So what we need to define a class of nice distributions. And this class of nice distributions has well, we use a particular but very natural class. We consider distributions which can be smooth. We have a smooth disintegration along unstable curves. So again, we don't have any manifolds, but the system is hyperbolic because it's a perturbation of an expanding map cross identity. So it's partially expanding to steal some the nomenclature from Roberto. And so you have a nice distribution which is given by this class of measures. So as an example, a very important example, in fact, you can consider any smooth distribution in the first variable and a delta measure on the slow variable. That will give you a nice distribution. So as a particular situation, as a particular case, the bag is obviously nice because unstable manifolds, unstable curves will be approximately horizontal. So you can always disintegrate the bag along such things as a smooth measure. Now, what is that we want to do? We want to study statistical properties, and we didn't, but we could have started to study the transfer operator associated to the system. But back then we had a different intuition, which is more physical, if you want. And this physical intuition is to leverage on a property of slow fast system, which is that they are very well suited to averaging. So what is averaging? So let me give you again a simple reminder what averaging is. So this is my map. I just copied it down here. And then remember, I have an invariant measure for each theta, which I call mu theta. And what I can do, I can consider the forcing here, and I can average the forcing for each fixed theta with respect to the equilibrium measure of the expanding map at that theta. Now, this gives me a function, omega bar of theta, which is the averaged field, if you want, which is felt by a point, and which is distributing according to a nice measure. And by whatever I said before, this is a smooth function of theta. So what's the idea here? The idea is that given the fact that I have two different scales at play, the expanding map will drive the system to equilibrium for each theta very fast. So whatever the distribution is, provided that it is nice, for instance, something like that, it will converge extremely fast to the invariant measure mu theta. And then once I'm distributed according to the invariant measure, well, this contribution kind of smears out and averages using the invariant measure. So this is essentially a natural object to look at. And we can define the average system, which is this blue thing over here, which is the solution of the ODE given by the following boundary problem. So you take the initial condition to be some theta star, and then what you do, you integrate the ODE, which is theta bar dot, equals to the average motion. So what can be shown, and this is again very somehow classical, what can be shown is that in fact the dynamics, the deterministic dynamics, converges to the average system. So how is in which sense this happens? Well, here it is, the precise statement. So this is essentially a law of large numbers. So for any, there's a typo here. So for any t positive, I define this function here. It's a random process. In fact, it depends on the initial condition. So for each initial condition, I can consider the evolution of the random variable theta n with this scaling. So for a given t, I consider epsilon inverse t. The integer part of this number will give me an iterate. And so if I want to plot this somehow on a discrete grid, I will have, this is t epsilon inverse, and then for each point over here, in a mesh of size, this would be each iterate, so this is size 1, I will have some points which are theta n given by starting from the initial condition x theta, and then what this function is, what this process is just a polygonal approximation of this quantity. So I just I do a very simple thing. I have a bunch of points. I connect them with segments. Okay, so this is a very crude approximation of my process. It is a Lipschitz function, so it has some smoothness, very weak smoothness property, but nevertheless, it is enough to be able to show that if you consider this process and you map, you send epsilon to 0, then this process converges in distribution to the average system up here. So as epsilon goes to 0, we will observe that if this is theta bar of t, then theta starting at the appropriate initial condition, then theta epsilon will approximate this in distribution. And in fact, much more can be proved. I'm not dwelling too much on this, but much more is true. Once you have a local limit theorem, sorry, once you, spoiled. Once you have a low large numbers, you can start working your way up into the hierarchy of limit theorems. We can prove a large deviation principle, and we can prove central limit theorem. And in fact, with Carlangelo in 2018, 16, 18, we proved a local central limit theorem for this system, which I will maybe have time to state vaguely in a little bit. And another thing which I want to notice and I want to convey is that, of course, you can average not just the dynamics, so you cannot just consider the average system with averaging omega, your driving field. You can take any smooth enough observable and compute, you see here, when you consider theta n, you're constructing essentially a Birkhoff sum of omega, so you can construct a Birkhoff sum of any smooth enough observable, and with due all changes which are due, you can obtain low large numbers for such systems for the observable as well, large deviation principles, and in principle you could obtain central limit theorems, although we refrain to prove that in our work. But for the sake of stating the results that I want to mention today, what I would like to do, I would like to just stop to the statement of the low large numbers and in fact state what the results are. So I have a couple of standing assumptions which I want to comment on. So so the standing assumption which we do, I want to make for this talk is that omega bar, which is again the driving average field, has zeros. So if you consider what this means, so you have an ODE, which is theta bar dot equal to omega bar, and let's pretend that omega bar has, say, just one pair of zeros. It has to be periodic, it has to be smooth, so zeros come in pair unless they are degenerate, but let's assume that we are always not the non-degenerate cases. So the dynamics of the average system is very simple to describe. You have every one of these two zeros of omega bar is a fixed point of the average dynamics. This one is an attracting fixed point, so this is a sink. And this one is a source. So for the sake of this lecture, I will assume that you have only one sink. And I will comment on whatever happens when you don't satisfy this. So you have, this is the main condition that I need to state my result. And then I also need some genericity conditions on omega, which I will comment on in a bit. Okay. Now, what is the statement of my theorem? So once again, this is due to two separate sets of people. One is myself and Carlangelo, 2016. And the other one is myself and Kasun Fernando, which was a postdoc here in Toronto, and now he was moving to Pisa. And this is still a work in progress, but this is at least nailed down. So what do we show? We show the following statement. Assuming epsilon sufficiently small, the map f epsilon admits a unique physical measure nu, which of course depends on epsilon, which satisfy exponential decay correlations with very precise estimate on the rate. So what does it mean? It means that if I take any two observables A and B, smooth or Holder, it doesn't matter, then this empirical decay correlation holds. You start from Lebesgue, which is your natural measure. You want to ask what is Lebesgue of A times B after the nth iterate. So this will converge to Lebesgue of A times the invariant measure, the physical measure nu of B, and it will converge exponentially fast as such. So you have a constant which of course depends on epsilon, on everything, on norms of A, the norm of B, the appropriate norms. And then you have this dependence on n with this C epsilon here, which would be the center, the spectral gap if we were using functional techniques. And here we have a very good somehow estimate on this rate. So this is nearly optimal. And in fact, we also get essentially the optimal one in this paper with Fernando. But in order to describe why this is the case, I need to dwell to dig a little bit further deep in the hypothesis, and I will do that by giving you a couple of remarks on this. So first of all, I need to tell you what the genericity assumption is. So one is a very natural genericity assumption, which is completely necessary unless we are after the general situation. So we don't want that omega, we don't want omega to be somehow a co-boundary, or rather more precisely cohomologon to constant. If this happens, the CLT, which we proved with Carlangelo, is degenerate, and as such, it's not very useful for anything. So this is essentially a necessary condition. And the second condition which we want is that the system has no zero Lyapunov exponent. So let me comment on this because it's kind of interesting. So of course the system is partially expanding, so you have at least a positive Lyapunov exponent, which is given by the expanding part. But then you have a center direction, and a center direction, you don't know what happens. So there are essentially three cases. The one is that you have, at the end of the day, zero Lyapunov exponents. This is something which we cannot deal with yet, but we know by the result by Castorini that at least in that case you have finitely many SRBs, and you have a spectral gap. You don't have any bound on the rate of convergence or the rate of decay or correlations, but that's tough to obtain, so that's totally fine. So in the negative center exponent situation, what we call mostly contracting, that's the situation that we studied with Carlangelo in 2016, and this is where we got this bound. But the new result, which is the other half of this pain here, is what happens when you have positive center exponents. So you have in a most expanding situation, and this is again this work with Kazum Fernando. And here we get essentially an optimal estimate for the rate of decay of correlations. So let me just give you a glimpse of why this situation is interesting beyond the fact that it's just the other half of the other side of the medal. So here you have a sink and a source. So according to the according to the law of large numbers, what will happen to most initial conditions is that after a time which is maybe epsilon log epsilon inverse log epsilon inverse, you end up distributed very close to this sink. And now you might ask, so how on earth is possible that if I'm continuing to be attracted to this sink, I have positive Lyapunov exponent? But that was a kind of a paradoxical situation in which we found ourselves, and this is what we studied with this paper, joint paper with Carlangelo, Poquet, and Volk. Well, it turns out that this is not exactly natural to think about, and the reason for this is that in this situation, the center foliation is not absolutely continuous, and this kind of goes beyond my intuition at the very least. And this is what is responsible for this paradoxical behavior of this sink, which is attracting, of course, for the average dynamics, but ultra-locally vectors which are centered in the aligned around the center direction will expand here. Okay, so this is the situation which we studied with Kasum. Now, I can just maybe say a couple of words about the case of several things, and then I think I have maybe 4 more minutes to give you an idea of the proof. At least according to my my clock. So the several sink situation is actually a very interesting topic in itself. We found the solution with Carlangelo in the case of mostly contracting system. This is very interesting because what we end up studying is a sort of deterministic Wenzel-Freitling system. So you have several sinks, and then each dynamics in a time scale of epsilon inverse is contracting everything into each sink. But then you have large deviations which can pull you out of the sink and bring you to another sink. So what we find is that in the most general situation, the convergence to the SRB, which might be not unique, is exponentially slow. So it's fast, it's exponentially fast with a rate which is exponentially slow in epsilon, because you need to consider the time scale of large deviations. And of course, we expect the same to hold in the mostly expanding situation, although we haven't worked on this yet. And of course, there's a question which is lingering in the back of my mind for the last few years. What happens when you don't have any sinks? So when you don't have any sinks, situation is kind of hard. The reason is you need to control the system for much longer time scales. You need to wait for the diffusive scaling to kick in to have any kind of mixing, because arbitrarily placed these densities won't converge to any sink in any epsilon inverse time. So we need to wait at least epsilon to the -2, and this suggests that the right time scale for these would be the right time scale. The right scale for the rate of decay of correlation would be epsilon squared, but of course we have no idea how to prove this. And if we are able to prove anything about it, it won't likely be this sharp. But this is what we expect at the very least. And now I might want to say maybe one word about the proof. This is perhaps due to the audience. So let me sketch what I want to. What's going on here? Of course, I am having issues in the last 2 minutes. Well, okay. So, oh wow. Okay, let me draw a picture. It's easier. So I have my system. So here are my sinks. This is my sink, and this is maybe my source. So this is the dynamics will be contracting over here. So what we have, we start from two densities. Let me draw maybe the support of these densities. One is red, the other one is blue. So after f to the epsilon inverse divided by log epsilon inverse iterate by the low large numbers, by the central limit theorem and whatnot, what we will find is that we are distributed very, very nicely along the sink. So this is the sink, and both of these initial distributions will be somehow very nicely, smoothly distributed around the sink, like so. And if you compute the marginals in the theta, you will see a very nice Gaussian here with scale which is root of epsilon. Now what you can do here, you want to use coupling, okay? So the flavor of coupling which we need to use is different if we have a contracting situation or if you have an expanding situation. So if a contracting situation, we use standard pairs and we couple along center manifolds, which has a whole bunch of problems, but at least it has a hope to work because the center dynamic is mostly contracting. So on average, I will get some contraction. In the expanding situation, we don't have this, I mean, the right tool to use are standard patches or plugs, which are essentially pieces of densities which are smooth in some sense. So they're smooth in the x, and they are so that they are smooth with an epsilon inverse modulus of continuity in the theta. And these patches you have an invariance lemma for these patches. Essentially, you will get, if you start from standard patches, you get standard patches. And then we leverage on the fact that this is a local diffeo to say that, okay, at some point you will have a region in which you have some overlap between a blue patch and a red patch. And now once you have a smooth density, or smooth enough density, and with distortion bounds, now you have two densities that get with overlap, you can just couple in the old-fashioned way, just at the same point, and these measures will be coupled forever. You don't have any problems whatsoever. So what we need to show is that this picture happens every epsilon inverse time, and that's what we do. So this was maybe a too fast sketch of the proof, but at the very least, I hope to have give you the idea of what the tools are. We don't use any functional tools. We use these standard pairs and standard patches, which is somehow a new-ish thing. So thank you for your attention, and this is it.
Thank you very much. Is there a question? Yes, please, go ahead.
Hi, thank you very much for the talk.
Thank you.
I was wondering if you don't have any condition on the derivative with respect to theta of the base map. It's always partial hyperbolic.
So as long as epsilon is sufficiently small, you can put yourself in a situation in which you are partially hyperbolic, right?
So
the dependence on theta essentially. So one thing that I should mention is the following. So this is the most natural situation to think of because it's not somehow paradoxical, but not only because of that. The most contracting situation is the situation which you have for a skew product, of course. And if you have a skew product or a perturbation of a skew product, you will always find yourself in this situation because somehow the change in theta of the family won't be enough to somehow dominate the averaging influence on the vectors. If we if you want to have a chance to see this mostly expanding situation, then you have to be somehow far away from a skew product. So to some extent, d theta, f theta should be not small, at least not small compared to something which I don't want to write down, but it should not be zero. I mean, this is something which is far away from skew products. Mm-hmm. So if you want to observe this paradoxical behavior, you want essentially the invariant measure to change a lot with theta. And this gives you some constraint in what f theta is, but it's not an explicit, it's not an explicit condition of f theta. It's rather an explicit condition on the contraction rate along the center, which has some kind of nice expression, but still it doesn't translate directly into what you can say for d theta f theta.
Thank you.
Thank you.
Thank you. I propose we move on to the next speaker. Let's thank Jacopo again.
Thank you.
And Jacopo, let me just show you the medal that you will receive as a token of appreciation for your invited talk. It will be mailed to you, if I understand correctly. Okay, so it's my pleasure to introduce the last speaker of this session, Anton Gorodetski. Anton received his PhD in 2001 from Moscow State University with a thesis written under the direction of Yuli Ilyashenko. And after a postdoc at Caltech, where he worked with Vadim Kaloshin, he moved to UC Irvine, where he's now a full professor. He has worked on a variety of problems in dynamical systems, including the non-removability of zero-Lyapunov exponents, the stochastic C of the standard map, and the question of how typical the Neuhaus phenomenon is. In addition, for more than a decade now, he has been one of the driving forces in the application of dynamical systems ideas to the spectral theory of Schrödinger operators. I understand this is the topic of his talk also. So in particular, he has worked with Victor Klepsin on a parametric version of Furstenberg's theorem, and then extended that to the non-stationary case. And so therefore, the title of his talk is Parametric and Non-Stationary Furstenberg Theorems and Angular's Localization.
Thank you so much for a nice introduction, and it's my pleasure to be here today. So today I'm going to talk about several results that some of them were published, some of them not yet. All of them were obtained. Well, something. Oh, cool. All of them were obtained jointly with Victor Klepsin from CNRS. So unfortunately, he's not here today, but this is how he looks like. And I want to start with a very simple question. So you take a matrix, just 2 by 2, a cell-to-R matrix, and you start iterate that matrix. How fast the norm of the matrix grows? So this is linear algebra 101. It grows exponentially. Exponential rate of growth is well defined, and it's exactly the logarithm of the spectral radius. Great. Let's now, okay, here it is. So let's now modify the question a little bit. Let's take several matrices. Let's just take two matrices for simplicity. And let's apply one of them or another and take the product, which is going to be a random product, and let's ask the same question. Let's take the norm of that product and see how that norm grows. Is it possible to claim that this norm has a well-defined exponential growth rate? It turns out that almost surely the answer is yes, and this is a famous Furstenberg-Kasten theorem that claims that this exponential rate of growth is well-defined almost surely, and that constant is known as Lyapunov exponent. Now, before I move on, I want to make a very first step in the proof of Furstenberg-Kasten theorem, which is actually a very simple one. We take a sequence and we call it subadditive if, well, that inequality holds. If a sequence is subadditive, then once again, this is an exercise in calculus. One can prove that for any subadditive sequence, the limit an over n must exist. And therefore, if I take expectation of the logarithm of the norm, then in our previous context, this is going to be a subadditive sequence. Now, this is not exactly what Furstenberg-Kasten theorem claims, because there we have much stronger statement, not only expectations on average converge, but point-wise we have convergence, but this is the first step. So I wanted to show that to demonstrate that even in this first step, it's important that all those matrices that we take are distributed exactly with the same probability measure, because otherwise you don't get a subadditive sequence here, and you already get into some troubles on the very first step. Okay, let's give some examples. Let's try to understand what that rate is going to be. Let's take two rotations, two simplest examples that come to mind when you consider SL2R matrices. If you apply that in random, there is no question about the rate of growth. There is no growth because when you apply several rotations, you still get rotations. The norm is 1, nothing happens. The Lyapunov exponent is equal to 0. Well, of course, it's cheating because we took rotations. So let's take instead hyperbolic matrix and say, I don't know, inverse of that hyperbolic matrix. What happens in this case? In this case, if you apply that randomly, then of course it can happen that you apply our matrix A randomly, I don't know, 100 times, and you will get a huge matrix. So it's possible to get a really large matrix here. But what is going to be the average rate of growth? If you just think about vertical or horizontal line here, then after you take a logarithm, it's equivalent to the question about the random walk on a line, and you know that you are going to go far away from the origin under this random walk, but on average you are going to be approximately root square of n far away from origin. So after you divide by n, you get 0. So Lyapunov exponent is again 0. Or let's take one hyperbolic matrix and one rotation. So you take hyperbolic matrix A as written and say rotation by 90 degrees. But once again, as soon as you apply this hyperbolic matrix many times, always there is a chance that you will swap stable and unstable directions. And then instead of expanding, you start contracting. And then you can see that again, Lyapunov exponent is equal to 0. Of course, all those examples are completely misleading, and the actual statement is that generically, the exponential rate of growth must be strictly positive, and that's exactly the statement of the Furstenberg theorem that was proved a little bit later. The conditions there, non-genericity conditions that are necessary, as we can see from those examples, are the following. First of all, if I take the smallest closed semigroup generated by my matrices in SL2R, then I want this closed semigroup to be non-compact. So roughly speaking, it's necessary for me to be able to grow in principle. You don't want to take two rotations or two matrices that are rotations in some coordinate system. And another condition is that you don't want to have finite set of lines such that this finite set of lines is invariant under each matrix in the support of your distribution. This is a condition that kills the second and the third examples. So obviously, this is genericity condition. So if you choose some matrices, to a couple of matrices really randomly, then they should satisfy this non-degenericity condition. And therefore, Furstenberg's theorem claims that in this case, Lyapunov exponent is going to be strictly positive. Now, first of all, I want to discuss the case when each of the matrices depend on parameters somehow. So let's take two matrices. Let's form our random product. We know that Lyapunov exponent is there and generically must be positive, but assume that each matrix depends on the parameter. So let's take a specific example. Let's take each matrix and compose it with rotation. So rotation is going to be the same. So after application of each matrix, I immediately multiply it by rotation, and the rotation angle is going to be my parameter. Now, let me now fix the sequence, random sequence of matrices. And only after I fix that random sequence of matrices, I'm going to start changing that rotation angle. So I have this random sequence that depends on a random parameter, on specific parameter. Is it true? So suppose that for each parameter, for each angle of the rotation, Furstenberg conditions are satisfied. So the Lyapunov exponent is positive. But is it true that almost surely I can claim that for all parameters, the Lyapunov exponent is positive? So can I swap the quanters in that statement? Now, intuitively, you immediately say, of course we can, because it's just a Furstenberg theorem after all. We have a product in the space of all sequences of matrices, We have a Lebesgue measure in the space of angles of the parameters. So almost surely we have a set of full measure where Lyapunov exponent is well defined and is positive. But notice that Fubini's theorem only tells you in this case that for almost every parameter that will be true. But is it true that for every parameter it's true or not? It turns out that, another example, and this is actually not a kind of toy example, but the actual motivation behind. If you consider a Schrödinger operator that is given by this explicit formula, then what you can do, you can take the potential being just random. Just think about a potential taking values, say 0 and 1. You just flip a coin and you get some random potential. So then, if E is an eigenvalue of this operator, then it means that we should have, well, this equation satisfied for each specific n, which means that we have some difference equation, essentially, that we're trying to solve, which means, as usually happens with difference equations, that we want to consider the sequence of matrices. And if you fix the solution of your equation at two sides, for n equal to 0 and n equal to 1, for example, then all others values of the sequence u of n are determined automatically. You just need to take the long product of those matrices that are usually called transfer matrices, and notice that those matrices are SL2R matrices. So once again, we're exactly in the context of the previous examples. We have a long product of SL2R matrices. Those matrices chosen at random because the potential is random, and those matrices depend on the parameter because energy E can be whatever parameter, whatever value. It can take any value you want. Great. So once again, the question, is it true that for all, with probability 1, for all energies, you have positive Lyapunov exponent? Notice that in this case, just due to the form of the transfer matrices, you automatically know that Furstenberg conditions are satisfied. So that's not a problem for any given value of the energy E. It turns out that, this is a question. It turns out that you can turn that, both of those examples into one framework. For example, you can say that you have some probability space, you have an interval of the parameter, you have a family of measures in SL2R parameterized by that parameter, and then you take the products of those matrices with respect to the measure given in that probability space, but now everything depends on the parameter. So this is just a way to formalize it in a unified way so that both of the previous examples work. And once again, the same question, is it true that almost surely you have that Lyapunov exponent positive, well-defined and positive for all values of the parameter? Now, it turns out that there are cases when the answer is yes, namely if you take the collection of matrices, let's for simplicity just think about finite collection of matrices for now, or even just two matrices. So if you have a collection of matrices which is uniformly hyperbolic, so the formal definition is given here, but intuitively you can think about the cone field, just not the field, just a collection of stable and unstable cones, such that those cones are stable and unstable cones for each of the matrix in your collection, the same cones for each of the matrix. Then you can see that any product of the matrices from your collection is going to be hyperbolic. You definitely have exponential growth. And in this case, if you consider SL2R matrices, then since you have just one-dimensional unstable direction, you know that what you do, you just integrate a specific function, and Birkhoff-Ergodic theorem tells you that for all the parameters, almost surely this Lyapunov exponent is going to be well-defined and positive. You can even show stronger things. You can show that Lyapunov exponent to be analytic with respect to the parameter in this case, and so on and so forth. Everything is nice. But maybe it covers everything. Maybe the cases when you have a collection of matrices that is not random, not uniformly hyperbolic, is kind of exceptional. This is not the case, and interesting way to see that this is not the case comes from spectral theory. In spectral theory, there is a Johnson theorem that claims the following. You have a dynamically defined ergodic Schrödinger operator. So just think about that ergodic Schrödinger operator that was presented there. Then the energy does not belong to the spectrum if and only if the corresponding Schrödinger co-cycle is uniformly hyperbolic. So in our particular case, you have that couple of transform matrices. Energy does not belong to the spectrum if and only if that pair of matrices is uniformly hyperbolic. And it's also known that the spectrum is a finite union of intervals. So there is an interval of the parameters where you cannot have uniform hyperbolicity. So you cannot hope to get uniform hyperbolicity by a small perturbation of the energy or parameter in general. So what happens if you don't have the uniform hyperbolicity? That's exactly what our first theorem answers. The conditions that we need are the following. First of all, we do want Furstenberg condition for all the values of the parameter. Secondly, how much time do I still have?
Maybe about 13.
Okay, thank you. So first of all, we need Furstenberg conditions satisfied. Secondly, we want everything to depend on the parameter nicely, which is not a huge restriction. Then we want uniform hyperbolicity to be out of the scope of our setting. And finally, we want the following. Whenever we change the parameter, we want the matrices to rotate every vector in the same direction. This is the most restrictive condition, most artificial one. Nevertheless, it does hold for a specific case, for both of the examples that we considered. For the second example, in order to make sure that it holds, you need, instead of one matrix, group the matrices in pairs, and for each pair it does hold, so it's not just a simple trick ensures that it does hold. Anyway, so under those three conditions, you can guarantee the following. First of all, you cannot guarantee that the limit exists, but you can guarantee that lim sup exists and that lim sup is equal to the expected Lyapunov exponent. So for each value of the parameter, Furstenberg theorem prescribes some Lyapunov exponent, and lim sup in this case is definitely what it prescribes. On the other hand, you will have some set which is going to be a dense G delta subset in the space of parameters where lim inf is going to be equal to 0. So if you consider the rate of growth, then from time to time, that rate of growth is going to be really, well, not impressive, let's say, which means that the Lyapunov exponent as a limit just is not defined. But fortunately, the set of parameters where it's not defined is going to be small. Not only it has small Lyapunov, small Lebesgue measure as Furstenberg, as Fubini theorem prescribes, it's also going to have small Hausdorff dimension. So that describes the picture. And as a byproduct of the proof, we managed to also see how those products of matrices behave. And as a result, we managed to find another proof of the Anderson localization. I will say a little bit more about that later. But it turns out that there are many different proofs of Anderson localization for Anderson-Bernoulli model. But we had the feeling that our methods actually really good. We could see much more than you can see with usual spectral methods. So we were trying to find some other setting where we could prove something that people didn't yet know. And that's how we came to non-stationary Furstenberg theorem. Now, here is the setting. What I want to do, I want to get as a product of SL2R matrices or SLDR matrices randomly, but randomness, the distribution, is going to be chosen in advance any way I want. So I have some collection of distributions, and for the first matrix, I choose one distribution. For the second matrix, I choose another distribution. For the third one, the third one, and so on. So you have a bunch of distributions, and after distributions are chosen, I can choose my matrices independently, but not identically distributed. I need somehow to mimic the Furstenberg non-degeneracy conditions. Now, you can translate the original Furstenberg conditions into the following. If you have the matrices, then there is no measure on a circle such that the projective maps, all of them, preserve that measure. Now, here we have different distributions, so it doesn't work, but another condition can work. So here's what we want. We want to make sure that for any of the distributions that we consider, it cannot happen that you have two different measures on a circle such that all of the matrices with respect to that distribution send first measure to the second, because that would be really something exceptional. So as soon as this non-degeneracy condition holds, we can guarantee the following. First of all, what I want to do, I want to take the expectation of the log of the product, of the norm of the product of those matrices. This is a non-random number, well defined. And in this case, we can say that lim_inf of 1 over n multiplied by this number is going to be positive, which means that you do have some exponential growth on average. After we proved that, it turned out that Ilya Golshade announced similar statement almost 20 years ago, and when we started to talk about it, he presented his proof, which turned out to be completely different, which is now also available. So there are two independent and different proofs of the statement. But this is not enough to apply for spectral problems. So we need much more. So we need the following. Not only we need to know that on average we have some growth, we need pointwise growth. So we want to make sure that this growth is well defined. But Lyapunov exponent is certainly not there because it doesn't have to exist. In principle, we have very different distributions. You can artificially easily construct the case when there is no chance for Lyapunov exponent to exist. Nevertheless, what you can do, you can say that this sequence of numbers, Ln that were defined already, plays now a role of Lyapunov exponent. Namely, if you remove those numbers from the log of the norm, then what you get is something that is going to grow not faster than linearly. That's exactly what you see here, and you can think about that in the following way. This is kind of a generalization of the law of large numbers. And law of large numbers certainly does hold for the random variables that are independent but not identically distributed. But you still need to subtract the expectations. So when you subtract this Ln, is roughly speaking, it means that you want to subtract that expectation, and then you get exactly the limits that you expect. Amazingly enough, not only this statement holds, but also you can prove that since we work with matrices, we want to say that if the matrix grows, then there is a vector that contracts with exactly the same rate. In general, it doesn't have to hold, but in this case, it does hold, so such vector does exist. And it's important because when you try to apply it to spectral problems, you want to say that there are eigenvalues. And to find the eigenvalue, you want to find the vector that is going to decay exponentially fast in both directions. And that's exactly what allows you to do that. Now, when you want to get all that together, parametric version, non-stationary version, and put it all together to non-stationary Anderson model, so you have a discrete Schrödinger operator where the potential is random independent but not identically distributed, then you get the following. You get that as soon as you have the randomness at each side, and assume that it's bounded. I think it's actually a technical condition. Probably it can be replaced by some finiteness of some momenta, but we didn't try to push it to the limit. And the fact that variation is bounded, uniformly bounded away from zero, means that you have some randomness present for each side of your potential. So the randomness cannot vanish. This implies that you have spectral localization, which means that you have point spectral for this operator. You also have dynamical localization, whatever it means. I will just mention for those who knows. And also, if you have half-line operator, both of those statements also hold. So that's essentially the new result. Notice that in case you take Anderson-Bernoulli model, when distributions are given without densities, then current methods current spectral methods actually do not provide this result, and this is something new for spectral theory as well. And finally, just a couple of opal questions. First of all, Furstenberg's theorem was considered by people as a starting point for random walks-on groups, and there is a huge theory there. But if you look at there, then all the results are specifically for stationary keys. You have some measure on a group, and then you pick the next element of the group randomly with respect to the same measure. And there is a reason for that. It's because the main tool in that theory is existence of stationary measure. And if you don't have stationary distributions, and it's not clear what to do. I believe that what we did opens lots of questions in that direction. So you can start working with random walks-on groups that are non-stationary. Another simple example, we proved an analog of large number theorem. In usual probability theorem, the central limit theorem also works not necessarily for identically distributed random variables. So I believe that the next natural question would be whether a central limit theorem works here. It's known that it works in the context of the standard Furstenberg theorem. In the parametric version, as I mentioned, I believe that it's not clear for us whether monotonicity that we require actually is important. It's used in the proof crucially. I don't know what happens if you actually start doing the dependence, if you allow the dependence on the parameter to be non-monotone. And it's an interesting question even dynamically, because just take a couple of diffeomorphisms of a circle, and suppose that one of them rotates to one side and another one to another side under the parameter, and try to draw the graph of the rotation number as a function of the parameter. So if you have monotonicity, then we know that what you get is the devil's staircase. If you don't have monotonicity, it's an interesting question. Now, we used, in some cases, we used that those are SL2R matrices, essentially. Some of the parts, non-stationary parts, we can generalize to SLDR case, but parametric part, it looks like the results are similar but still different. Finally, you can easily replace projective maps of circles by general diffeomorphisms or homeomorphisms of circles. So Furstenberg's theorem does hold in that context. So synchronization properties for random groups of random applications of semigroups of diffeomorphisms or even homeomorphisms are known. So some of them were proven by Klebs and Nansky, some of them were proven by Melisset. So there are some results in that direction. So what happens if you start doing similar things in the parametric or non-stationary case? So that's where I want to stop. Thank you very much.
Thank you. Okay, are there any questions? Yes, please.
Yes, so I just wanted to say that the problem you handle with your parametric theorem also appears naturally when you study statistical stability of random dynamical systems. It appears when you want to study the oscillated spaces of the transfer operator associated. So do you have any idea if your method also applies in infinite dimensional setting.
Possibly, but I cannot be absolutely confident. But we can maybe talk later about it.
Yeah, sure. Thank you.
Any other question? Yes, please.
In the statement of spectral localization, why the boundedness of the random variable is required? Or the potential, I mean.
So for us, it's just for convenience.
Okay.
There are generally, so, okay. First of all, in the classical Anderson model, the results only require existence of some moments. I believe that in the case of Anderson-Bernoulli model, they just require existence of some of them. So I also believe that in this case, similar results should work. But for us, just technically, we already had so much in our hands that we didn't try to extend it to that direction. But I do believe that it actually does hold.
Thank you very much.
Okay, so let's thank our speaker again. So first of all, let me present you your medal.
Thank you so much. And also, I believe this is the last session, and so I would suggest to thank the organizers. Sometimes for people who works in dynamical systems and in some area of mass physics, they kind of feel like they fall into the gap between the areas, and I would like to thank the organizer for filling this gap by this session.
Okay, so, and in fact, let us thank all the speakers of the invited and contributed talks for really excellent lectures. And all the participants and people that attended talks and participated. So with this, I would like to conclude our thematic session. Thank you.